Okay, so I will continue with part two. This part will be mostly about applications of the monopole Lefschetz number. I will start by defining a concordance invariant for not using this monopole Lefschetz number. Then I will use this invariant to investigate the question that when is an n-fold branch cover over not an L space. The discussion will be divided into two parts. When n equals 2 and when n is a general even number greater than 2. In the first case, the Lefschetz invariant provides a obstruction, and in the second case, the Jones polynomial actually provides an obstruction. Okay, so let me start by defining the not invariant Lnk. From now on, we will just take our knot be a knot inside a 3-sphere. And for n greater or equal than 2, we will denote the n-fold cyclic branch cover of S3 with branching set k by this sigma nk. And we will let F be the covering transformation, or more precisely, F is the deck transformation that generates the group of covering transformations. And now we can define a not invariant as the Lefschetz number of the induced map on the monopole Floer homology. So this is just an integer. And from its definition, it's pretty clear that it's a not invariant. It only depends on k. But what's less obvious is that this invariant is actually a smooth concordance invariant, and it's actually additive. Okay, to explain this, well, so let's assume sigma nk is a rational homology 3-sphere. This is always the case when n is a prime power. And then our main theorem actually implies that this Lnk is just this linear combination of the Lefschetz invariant and the signature. So here S is the unique is the unique spin-C structure that is invariant under the covering transformation. And as I said in part 1, this is the Tristan-Levin signature. Okay, and also recall that two knots are K0, K1 are smoothly concordant if they together bounds a smoothly embedded annulus in S3 cross I. So studying smooth concordance is one of the most important questions in modern knot theory. And note that both the Lefschetz invariant of the branch cover and the Tristan-Levin signature, they are concordance invariant. Namely, if two knots are smoothly concordant to each other, they have the same Lefschetz invariant and signature. And they are both additive. And as a corollary of this formula, we see that when n is a prime power, this invariant coming from monopole Lefschetz number is actually a smooth concordance invariant. And furthermore, it's additive. That means if you take the connected sum of two knots, you evaluate Ln, it's just the sum of the invariant of each knot. And this provides us a useful invariant to study knot concordance. And okay, and it turns out that this invariant has some relation with the L-space conjecture. And well, let me recall the statement of L-space conjecture anyway. This is a famous conjecture. Okay, so a string manifold sigma is called an L-space if it is a rational homology sphere and it satisfies this vanishing condition on the reduced monopole Floer homology. Okay. Well, since we know that monopole Floer homology is the same as the Higa Floer homology, so so equivalently, sigma is an L space if and only if the hat version of the Higa Floer homology has minimal rank, namely the rank of the hat version Higa Floer homology equals the element in the first homology group of your sigma. Okay, so that's the classical definition of the L space. Okay, and from the perspective of Floer homology, those L spaces are the simplest three manifolds because they have a very simple Floer homology. And for example, we know that any positive scalar curvature metric three manifold are L spaces, and there are a lot of there are also a lot of hyperbolic examples. But well, but from the perspective, from our perspective, these L spaces are not simple at all. Namely, we don't really have a classification theorem for all L spaces. Okay. And in this direction, there is this famous L space conjecture by Boyer, Gordon, and Watson. It states the following: suppose sigma is an irreducible rational homogeneous three-sphere, then the following three conditions are equivalent. First, sigma is not an L space. Second, the fundamental group is not left-orderable. And third, sigma admits a co-orientable Taut foliation. Okay. And while this conjecture is still open, but there are some important cases that are known. Okay, for example, when the three manifold has a geometric structure and it's non-hyperbolic, then the work of Boyer, Gordon, Watson actually shows that this conjecture is true. That includes all cipher three manifolds. Okay. And and the second case is the graph manifold, and in this case, the work of Hanselmann, Rasmussen, and Watson also confirm this conjecture. And also note that actually 3 implies 1 actually holds for any rational homogeneous three sphere. That's the only part of this conjecture that we know in full generality. And it's due to Audra-Zabel in the context of Higa-Floer homology, and due to Kohlhammer-Morovka Audra-Zabel in the case of Monopole Floer homology. Okay. And well, so in order to, so in this talk, I want to use this invariant LNK, the monopole Lefschetz number, to study this, to investigate this conjecture. And so let's specify to the case of n-fold branch covers. Recall that by a very classical result of Audra-Zabel states that when the branch double cover sigma 2k is an L space when k is closely alternating. Okay, they prove this using Z triangle in Higa-Floer homology. And furthermore, we also know that suppose K is Coan of sin, and then the branch double cover is also an L space. So this is due to Audra-Zabel in the context of Higa-Floer homology, and due to Jonathan Bloom in the context of Monopole Floer homology. Here, sin means that the reduced Coan homology is supported in a single delta grading. Okay? So that means the Coan homology is small as possible. Okay, now then we have a pretty natural question one can ask in general: given not, when is the n-fold branch cover an L space? Okay. So a previous result by Audra-Zabel and Bloom basically give us a lot of examples of branch coverings, a twofold branch cover being L spaces, and it's natural to ask what happens in general N. And this question is interesting by itself, but it's also a very interesting test case of the L space conjecture. And actually, Gordon and Liedman wrote a paper to start to investigate this question, and they actually study a large family of knots, many examples. Okay. And well, so we want to use the monopole Lefschetz number to investigate this question. And by definition, if sigma nk is an L space, then the reduced monopole Floer homology is just vanishing as a result. So trivially, the Lefschetz number must equal 0. So we see that this not concordance invariant actually equals 0 whenever the branch cover is an L space. Okay. And furthermore, we have this formula, we have this expression that expresses this LNK in terms of the Floer invariant and the signature. So this actually provides a connection of this question to the classical invariant, namely the Tristan-Levin signature. And also note that the recent work of Dunfield and Rasmussen actually relates the left orderability of the branch cover to also to Tristan-Levin signature. They did this by defining a new invariant called the SL2R Casson-Lin invariant. So, well, in light of the L-space conjecture, it will be very interesting to see if there is some deeper connection between our result and Dunfield-Rasmussen's result. But still, we don't know what's the precise relation between them. Okay, so let me give the precise statement, and I will divide the discussion into two parts: the case n equals 2 and the general case. Okay, so let's start with the case n equals 2. When n is equals 2, our formula read as that L2k is just negative the Floer-Hopf invariant for the spin structure plus the signature over 8. So signature, this when this index equals 1 over 2, this Tristan-Levin signature is just a classical knot signature. Okay, and as a corollary, we see that given a link, suppose the branch double cover is an L space. For example, when a link is Kohanov thing, then 4 times the Floer-Hopf invariant actually equals the signature. Okay. We actually prove this corollary in a slightly more general setting, namely we consider all links, not just knots. And actually, this confirms the conjecture made by Manolescu ovens, and they prove this conjecture in the case of alternating knots, and they conjecture it for quasi-alternating, for all Kohanov thing knots. And this corollary actually generalized previous result, in which case L is a quasi-alternating knot. Okay, so Manolescu ovens, they prove the conjecture for alternating knots, and then Donut ovens, they prove it for alternating links, and then Liska ovens prove it for quasi-alternating links. Okay. All right, and that's the case n equals 2. So let's move on to the general case n is greater or equal than 2. In this case, well, the most natural thing to do is just say, okay, Lnk is non-zero, so that gives some direct obstruction of the branch cover being an L space. Well, this actually works, and it gives us, let me give some interesting example. Okay, so we let K be a knot which is smoothly concordant to a torus knot, TPQR. Then actually, then for any prime power n, such that first NQR are co-prime to each other. 2, NQR is not a permutation of 2, 3, 5. Then using this monopole Lefschetz number, we can conclude that the n-fold branch cover is not an L space. So that means this not being an L space result sometimes holds for the whole concordance class. This is because Lnk actually equals the corresponding invariant for torus knot. And for those torus knots, since the covering transformation are smoothly isotopic to the identity map, the monopole Lefschetz number is just some kind of normalized Euler number of the branch cup of the monopole Floer homology, and that can be computed directly. So that's non-zero. Okay, and I also note we also note that for this example, we only use part of the information. Namely, from the fact that the monopole Lefschetz number is non-zero, we conclude that the reduced monopole Floer homology is non-vanishing for the unique spin C structure that is invariant under the covering transformation. This spin C structure actually comes from some spin structure. Okay, and we didn't use any information from those other spin C structures that are switched by the covering transformation. Okay, and so that's the case. That's one direct obstruction. And using a slightly indirect argument, we can also prove another obstruction. the general case when n is an even number. Okay, so let me state the theorem. Suppose we have a not k with determinant 1, and suppose the derivative of the Jones polynomial evaluated at -1 is non-zero, then then sigma 2mk, the evenfold branch cover, is not an L space for any positive integer m. Okay, so m can be 1, can be 2, can be any positive integer. Okay, and this result gives a systematic obstruction of higher branched covering spaces being L spaces. And it will be quite interesting to compare this result with recent result of Boileau, Boyer, and Gordon. Last year, I think they proved a result that a structure of Alexander polynomial actually can also be used to obstruct the branched cover being an L space when k is quasi-positive. So you can see that actually both Jones polynomial and Alexander polynomial appears in this story. Okay, and before sketching the proof, let me just give you some idea. Okay, the idea is to consider the covering transformation for the branch cover, of course, but trick is to apply the monopole Lefschetz number not just to this covering transformation, but also to the square of it. And by doing this, we get two different expressions of the Floer invariant, and we can use them to cancel the Floer invariant. We don't want to deal with the Floer invariant of the branch cover in general because that's kind of hard to compute. Okay. All right, so yes, so let me start the proof sketch. Okay. Well, so it will just be proving by contradiction. So suppose sigma 2 mk is an L space. Then both the monopole Lefschetz number of the covering transformation and square of the covering transformation, they are both zero because the reduced monopole Floer homology is zero. Okay. And now we apply our monopole Lefschetz number to both f and f squared. We get two expressions of the Floer invariant of the branch cover. Here, n should be just 2m. And the first expression expresses this Floer invariant just in terms of Tristan-Levin signature of the knot. And the second one actually expresses this Floer invariant as m times the Casson invariant of the branch double cover. And plus 1/8 the Tristan-Levin signature of knot inside the branch double cover. So we have branch double cover is because if you quotient out this sigma 2m by f squared, you don't get S3. Instead, you get sigma 2k. Okay? So we get two different expressions for Floer invariant. They must be the same. And therefore, we get this interesting relation between the signature of knot inside S3, the Casson invariant of the branch double cover, and the signature of the knot in the branch double cover. So this is the relation we just deduced. And the next observation is that the cipher matrix of K in S3, if you take the square of it, you just get a cipher matrix of K inside the branch double cover. Right. So, and essentially using this relation and some linear algebra, you can deduce that the signature of K inside S3 and the signature of K inside sigma 2K, they are related to each other by this additional term, which is m times the classical signature of K. And using this, plugging this relation into this into this formula we just get, we obtain this simple relation that suppose sigma 2mk is an L space, then the Casson invariant of the branch double cover equals 1/8 signature of the knot. Okay, so it's kind of interesting to see that, you see, 2m for branch cover doesn't appear in this relation. This relation is purely about the true for branch cover and the signature. Somehow the sigma 2mk just and all the information get canceled in this relation. Okay? And then we use the following theorem by Mullins. This theorem states that for any knot inside S3, you take the Kasson-Walker invariant. It's just the 1/8 signature minus 1/12, the derivative of the Jones polynomial. In our case, since we assumed our knot has determinant 1, so the branch double cover is an integer homology sphere. So the Kasson-Walker invariant is just a Kasson invariant. So we can use this result to combine this result with this equality we just get to conclude that the derivative of the Jones polynomial must be vanishing. And that's the contradiction with our condition. And well, so a quick explanation of this theorem is basically, well, so how does Jones polynomial appear in this obstruction? Basically, by Mullin's work, Jones polynomial is related to the Kasson invariant of the double branch cover. And the Kasson invariant by the work of Lim and Chen, so they are actually related. They're actually equal to some normalized count of monopoles on 3 manifolds. So by these 2 steps, actually Jones polynomial come into this story. Okay? So that's the sketch of the proof, and I think that's all I want to say today. Thank you.